All right, so in this lecture, we talk about vectors and dot products. So we're going to, the objective of this lecture is to define and evaluate dot product between two vectors. Find the norm or the magnitude, right? Another name for the norm is the magnitude or the length of the vector. Determine the angle between the two vectors using dot products. Integrate the dot product geometrically and find the projections and component of projections of one vector onto another vector, right? And toward the end of this lecture, we will look at one applications of dot product. Okay, so because I strongly believe that you have gone over this material in multivariable calculus and also in linear algebra already. So I'm going to spit through the definitions and all the properties. But stop me, okay, or slow me down if you have any questions. All right. So scalar is the physical quantity that only have the magnitudes, right? So the example for that is we're talking about the length of something, the height of something, of the weight, the width, the area of something. Now for vectors, also the physical quantity that have both magnitude and directions, right? We're talking about velocity, acceleration, force, momentum, so on, so forth. Right. And so in this, let's start with something, sorry. So let's stick with some notations for vectors, right? So this arrow right here represents a vector. Okay. So you have this one is the initial point. Right. And we call this a tail. The tip of the arrow is called the terminal point or the head. For general vector, we usually use the letter U, letter V, letter W, A, B to indicate vectors, with the arrow on top to indicate that there are some directions as well. But certainly you can use any letter, but by convention, usually we just use we use U, V, W, A, B, X, Y, so on and so forth. So that's the general vector. When we talk about unit vector, you have, let's say I have a unit vector U is equal to the unit, the vector V divided by the magnitude of the vector V. So in this case, this notation indicates the magnitude or the length of vector V. So I use two vertical lines on each side of the vector, but so this is the notation that I use for norm or magnitude, but certainly you can use this notation as well. Okay, you can have seen them both ways. You good with that? Okay. So let's move on to the component of a vector. So we're talking about 2-dimension, 3 dimensions, or n-dimensional vectors. So in 2 dimensions, you have vector U equal to U1 and U2. Or you can write like this, U1, U2. So this is called the row vector. And this is called the column vector. Sometimes it can also be written as
Right, so u is equal to u1 I hat plus u2 j hat.
So this form is called the standard unit vector form. Because you have unit vector, standard unit vector in your representation.
So that's 2 dimensions. In 3 dimensions, you just add one more component in the vector. So you can write u equal to u1, u2, u3, or you can write u equal to, I can use my in writing column
Vector, you can either use
or you can describe the vector u as u1 times I hat plus u2 times j hat plus u3 times k hat. So for n-dimensional vector, you write u equal to u1, u2 up to un. You have n component of vectors. Or you write u equal to u1, u2 dot 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 un. And in the standard unit vector forms, you have u equal to u1 times e1 hat plus u2 times e2 hat plus un times en hat. Right, so hopefully you remember this notation from the previous courses. Any questions on the first page of the lecture notes? Good. Now move. Am I moving too fast? Good. A little bit. Yes. A little bit. So we have been talking about unit vector. We're talking about the magnitude of a vector. Now let's go into a little bit more detail of these definitions. All right. So let's talk about the norm or the magnitude or the length of a vector. So the length or magnitude of a vector v equal to v1, v2 up to vn in Rn is, so the magnitude is written as square root of v1 square plus v2 square dot 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 plus vn square. So that's how you find magnitude of the n-dimensional vector. Now for the unit vector, we wrote that formula earlier, but doesn't hurt to rewrite it again here. So for any non-zero vector v, the unit vector u of v is given as, so the unit vector u is equal to vector v divided by the norm of the vector v. That's how you find a unit vector. So because it's called the unit vector, the length of any unit vector is always equal to 1. the length of U is equal to 1, or let's say that the magnitude of any unit vector is 1.
Now, because the calculations of U depend on vector V, whatever the result you got for U, you always have the same directions as V. And the equation we wrote down here, I call that equation 1. So equation 1 is called equalization. So in three-dimensional space, you have the standard unit vectors, right? So I is the standard unit vector for x directions, j is the standard unit vector for y direction, and k is the standard unit vector for the z directions. So here, if I zoom in, so I have this is I, sorry, this is I. We use a different color here. So I had equal to 1, 0, 0. This is j hat. This is 0, 1, 0. And this is k hat 0, 0, 1. So I, j, and k call the standard unit vector. What time do we go? I forgot. I have another class after this, so I just want to make sure. 12:15. Okay, thank you. Okay, so now you have a vector, you're given a vector, you can manipulate that vector. It's in a scalar. You can extend the vector, compress the vector. You can extend the vector or compress the vector and then change the directions of the vector using the scalar. Okay, so that's what we're going to do in these definitions. So a product of k times v of a vector v and the scalar k is a vector with a magnitude that is absolute value of k times the magnitude of v. Okay. And depends on the value of k, you can extend or compress the vector and also change the directions of the vector. Okay. If k is positive, k times v has the same directions. As vector v. But if k is less than 0, then k times v has the opposite directions. As v. Right, so as you can see in this image, you have the original vector v, then you can extend v, fine, make it longer, you can longer than the original vector, or you can make it shorter. Or you can change the directions of the vector v.
So there are some definite, some properties of vector addition and scalar multiplication. Or again, all of this property you have seen, you should have seen that in multivariable calculus and linear algebra. So the first one is the property u plus v is equal to v plus v. That's commutative property. So this one is commutative.
The second one saying that if you group v and w, do that calculation first and then add the u later. It's going to be equivalent to u plus v plus w.
So this is associative property of vector additions. So associativity.
Number three, show that zero is an identity of vector addition. So u plus zero equal to zero plus u equal to u.
Can you change that, please? So this should be an equal sum. So this is called additive identity property.
Number four, u plus negative u is equal to zero.
So this is additive inverse property.
Now, number five, let's say you have a vector u in two different scales. We say that if you apply the scale d and then the scale c is equivalent to by applying the scale c and then d, or manipulating the scale, then apply that new scale to the vector u. Those are equivalent.
And this is called the associativity of scalar multiplications.
Number six,
You have again two scale, but in this case, you distribute the vector u into the parenthesis. This is called distributive property of scalar multiplication.
and you have the same name for property seven. Okay, even though you just have one scale, this still the process of distributing C onto U and vector V.
So this two on distributive properties of scalar multiplications.
The number eight, you have one times the vector U, it's just the vector U. So this multiplication is the regular multiplication. So one.
And this is called the identity property of scalar multiplications. And again, this is regular multiplications. And the last property is the zero property. If you have a zero scale, then multiply with the vector u, then you have a scale zero back. Again, here you have regular multiplications. So I have another typo here, but bear with me. I'm gonna explain to you before we make the change. So let's say U is the three-dimensional vector. So you have U1, U2, U3, then zero in the front. This is the regular multiplications. So usually when you do the calculation of this type of multiplication, you just do 0 times U1, 0 times U2, and 0 times U3. You with me on that? So therefore, you should have 0, 0, 0, and this should be a zero vector. Can you change this instead of just the scale 0, this should be a zero vector. Does that make sense to you? Good. All right. Now let's move on to the next topic, or the main topic of this lecture is the dot product. So I'm gonna give you two n-dimensional vectors, and I'm gonna give you the formula to calculate the dot product of the two vectors. So consider vector u equal to u1, u2 up to un, and vector v equal to v1, v2 up to vn in Rn. Then the dot product of u and v is calculated as so u dot with v is equal to u1 times v1 plus u2 times v2 dot plus un times vn. For short, this is equal to the summations of u sub I times v sub I for I going from 1 to n. So one property of this dot product is that the dot product of the two vector is invariant under rotations. Is invariant under rotations. So that means that if you have the dot product of two vectors u and v, if you rotate both of them at the same time, the result should be the same, no matter how you rotate the two vectors at the same time. Now let's take a look at the properties of dot products. Given three different vectors u, v, and w, and the scalar c. So the first property is the commutative property. So u dot with v is equal to v dot with u. the result is always going to be a scalar, so no matter the order of u or v, the answer should be the same. So this should be commutative. Commutative property. Now you have u dot with v plus w. You can distribute the vector you want to parentheses, and you have u dot with v plus u dot with w. So it's called the associative property. Oh, sorry, distributive property. Number 3, you have vector 0 dot with vector u is equal to vector u dot with vector 0. You should have the 0 vector. Sorry, the 0 scalar. Should be a scalar. That's why the dot product has another name. It's called the scalar product. And this is 0 property. The next one is this formula is the formula that connects the magnitude with the dot product. So the magnitude square of the vector is equal to the dot product of the same vector. So this is magnitude in terms of dot product. The last property say that now we have two vectors, you want to do the dot product and then apply the scale on the results. You can do that, or you can scale one of the vector first and then apply dot product. It's going to be the same. Got it? I couldn't find the name of this. Okay, so that's the definitions of dot product, give you the idea how to calculate the dot product of two vectors, some properties of the dot product. We're gonna move on to interpretation of the dot product, right? So the dot product allow you to calculate the angle form from these two vectors. So if theta is the angle between u and v, then u dot with v is equal to the magnitude of u times the magnitude of v times cosine of the angle between the two vectors. Or more specifically, to calculate the angle between these two vectors, you do cosine of theta equal to u dot v divided by the magnitude of u times the magnitude of v. So let's quickly prove this theorem. It's very straightforward proof using the information that we learned from the past. All right, so here's the setup. We'll take a look at the image here. So you have two vectors, vector u and vector v. These two vectors form an angle, called this angle theta. And you have another vector here, is vector u. Okay. So first approach is to use the law of cosine on the vector difference. Right, so use the law of cosine to get one. So the magnitude of u minus v square is equal to the magnitude of u plus the magnitude of v minus 2 times the magnitude of u times the magnitude of v times cosine of theta. In addition, we get that the magnitude of u minus v square. Okay. So this u minus v, magnitude of u minus v square, we're gonna apply one of the property that we see earlier here. So more specifically, number 4, property 4 right here, that relate magnitude in terms of the product, write the magnitude in terms of the dot product. So here you get u minus v dot with u minus v. So here you use property 4 of theorem 1. And then you use distributions for the next step. Right, so we just FOIL this out. So u dot with v minus u dot, sorry, u dot with u minus u dot with v minus v dot with u plus v dot with v. Again, I just use distributions. Right, so u dot with itself is the magnitude square. V dot with itself is the magnitude of v square. And these two terms are the same, so so you get the magnitude of u square minus 2 times u dot with v plus the magnitude of v square. So using the law of cosine, I form one equations. I call this equation 1. And using all the properties of the dot products, I form another equation and call this equation 2. Right. So this equation is the magnitude of u minus v squared. I call this equation 2. And I'm going to let 1 equal to 2. We obtain that on the left hand side, you got the magnitude of u plus the make some mistake again. For the law of cosine, this should be u squared, the magnitude of u squared, plus the magnitude of v squared, sorry. So for the first equations, you have the magnitude of u squared plus the magnitude of v squared minus 2 times u magnitude of u times the magnitude of v times cosine of theta equal to the magnitude of u squared minus 2 times u dot with v plus the magnitude of v squared. So I can cancel this terms out. And I left with negative 2 times the magnitude of u times the magnitude of v times cosine of theta equal to 2 times u dot with v.
And now to get cosine of theta by itself, I divide both sides by negative 2 times magnitude of
U and magnitude of v. So cosine of theta now equal to u dot with v times the magnitude of u times the magnitude of v. And that's the proof.
Okay, so this formula, again, calculate the angle between the two vectors, through the dot product, right? And you know that from this equation, it's allowing us to see how the two vectors are going to behave with respect to each other. Right, so if they are form a 90-degree angle, then the dot product is going to be, or cosine of 90-degree angle is 0. Therefore, the dot product is going to be 0, right? So that is corollary of this, the dot product, right? Which allow you to test the perpendicular between the two vectors or orthogonal between the two vectors. So two vectors u and v are orthogonal if and only if u dot with v is equal to 0. So again, using the formula cosine of theta equal to the dot product divided by the magnitude of product of the two vectors. This tell you, the dot product tell you measure how similar or how well the two vectors travel together, right? So if the vectors are parallel or travel in the same directions, the dot product will be as big as possible, or either negatively or positively big. So for example, if u and v point in the same directions, in this case, this is the two vectors pointing in the same directions. We're going to get that u dot with v is equal to 1. And the angle formed from these two vectors is going to be equal to 0. And so theta is equal to 0 degree or 0 radian. Again, if u and v point in the same directions, we have that u dot with v is equal to 1.
So if U and V are pointing exactly opposite direction of one another. For example, in this case, right here, then you have that U dot with V is equal to -1, or in this case, the angle between the two vectors is going to be 180 degrees, or pi in radian. Now let me go up here and write that U and V point in exactly opposite directions, then the dot product is equal to -1. Now, when you do the calculations and you get that the dot product give you a positive number, then U and V are pointing in the same directions. Right, so for example, in this picture, the two vectors have pointing in the same direction and is forming something called the acute angle. U dot with V is positive, theta is an acute angle. Or theta is going to be between 0 and pi/2. Now, when you calculate the dot product and it's give you a negative value, then U and V are pointing in the opposite directions. So you have U dot with V less than 0, or theta in this case, the obtuse angle. Or theta is between pi/2 and pi. We good? Okay. Any questions so far? All right. So one fun application of the dot product is how you place the solar panel on the roof of a house. Okay. So this is my solar panel right here. It's facing upward, right? I laid out flat on the table, so the panel facing upward. So that means if the sun is right here, so this direction is for the panel. If the sun is right here, then the sunlight is directly this directions, right? So it's formed 90-degree angle, right? So therefore, there's no energy consumed. So that is 0. If you have this, the sun is right here at this angle right here, right? So therefore you're going to collect some energy as in the two line kind of parallel. Okay. If the sun is right here at this angle, right, collect some information, some energy here. If the sun is here, it's collect some energy, right? But not a lot, because if the sun is going in either this positions, move to this positions, right, then you have no energy collected. Okay. So therefore, most of the time you see the solar panel is always placed as an angle so that it can collect the most energy from the sun. So that's one of the applications of dot product. Good. Okay. The better approach for this type of solar panel is with the remote or with the setup depends on the day, the time of the day, right? So during the morning, it can be placed in this, right? In this angle, and then when the sun moves to over here, it is placed this angle, so with the time setup. So that's a cool application, I think. Now, what time is it? Okay, so let's write down some more information about the projections of from one vector to another vector. So consider two vectors u and v with the same initial point, right? So the setup is going to be like this. So you can have these two vectors. Two vectors with the same initial points. So the scalar projections of v onto u, this is v. The green one is u. So the scalar projections of v onto u is called this is so scalar projections is equal to u dot with v divided by the magnitude of u. And this is called, the notation for this is a little bit weird, com of v onto u. Okay, let's write down the formula first. I will derive the formula in a minute. Then the second definition is the vector projections of v onto u. So vector projections is equal to u dot with v divided by the magnitude of u times u divided by the magnitude of u. And this is the projections of v onto u. All right, so I have 5 more minutes. Let me write quickly derive the formula for the scalar projections. All right. So let's take a look at the first image. Again, the setup is that I have a vector u, vector v, they have the same initial point, so they can point a theta. The process is that I'm going to project this vector v onto vector u. Also the projections vector, it's just the shadow that we see of v onto u. And this shadow is that right here, and I'll call the magnitude, call magnitude x. So here, this is the angle theta. This is x, right? Just the shadow. So what I do is I let theta be the angle between u and v. Now I'm going to calculate the cosine of theta. So cosine of theta is equal to the adjacent over the hypotenuse. So the adjacent in this case is x, the magnitude of the red vector. So x over the magnitude of v. So from here, you can write that x is equal to magnitude of v times cosine of theta. Now, using the dot product, you can rewrite cosine of theta using a different formula. But cosine of theta is equal to what? U dot with v divided by the magnitude of u times the magnitude of v. Then you substitute this formula for cosine of theta into this equation with x. Then you have that x equal to the magnitude of v times u dot with v divided by the magnitude of u times the magnitude of v. And you can cancel out the v, the magnitude of v, right? And you left with just u dot with v divided by the magnitude of v, sorry, the magnitude of u. Right. When you apply the projections of a vector onto another vector, we are having a shadow. Right? And these calculations give you the length. And this is called the component of v onto u, or the scalar projections of v onto u. And to calculate the vector projections, the vector is in the same directions as u. Therefore, we multiply with the unit vector. Let me stop right here. I will continue with this on Thursday. One thing on Thursday, can you bring your computer with you on Thursday so we can talk about the LaTeX project? Okay. Thank you for being here, everyone. You have a good day. Okay.